Hello everybody, this is 5.4 indefinite integrals and the net change theorem. So we need to distinguish between a definite and indefinite integral. So in this section we introduce a notation for antiderivatives, review of course some formulas, and reformulate that second part of the fundamental theorem of calculus in a way that's easier for some or actually many applications. So looking back at this FTC, the first part, it says, of course, that if f is continuous, then that integral is an antiderivative of f. And the second part says it can be found by doing f of b minus f of a. So, of course, for this presentation, you want to see the previous lecture video or notes, where f or capital F is the antiderivative. We need, of course, some convenient notation, and let's see that. So if we look at this integral of f of x as this equal to this antiderivative f, that means as f prime, capital F prime equal f. For example, the integral of x squared equal to x cubed divided by 3 plus c. You see, this is not a definite integral, so we're not doing f of b minus f of a, where the c kind cancels out or doesn't show. So here, something to observe, when this is not indefinite, you're getting a general formula, so you're getting like a function, where when we did examples, when we did something like this, we can try it here for x squared. And let's say 1 to 2 dx. It's going to be x cubed over 3. Right? It's going to be 1 to 2. So that's 2 cubed. Let's put the third here. That's a 2 cubed minus 1 cubed, which is 1/3, 8 minus 1, so a 7/3. If you see, when this is definite, you're getting a number, right? When this is indefinite, you're getting like a function. So that's a major difference between the two. And that's, I think, the comment here to distinguish that idea between the definite and indefinite integral. So if you have formulas, of course, you just go back to that table or formula sheet if you don't recall what it is. But with practice, you should memorize many of these. So if we have for secant square, the integral is going to be tangent x plus c. Why? Because the derivative of this tangent x plus c is secant square. And this is the table, adding a c because of a general formula here for these integrals, right? And you've seen now this one a few times. So we adopt this notation. So that's that. Why? Because if you differentiate this, you will get 1 over x squared. So this is true despite the fact that that the general antiderivative of the function is, of course, two different constants if x is less than 0 or if x is greater than 0, because the constant that is existing in x is less than 0 is not going to be the same that the constant that it's going to be when x is greater than 0 because of this x squared, but still this is still true despite that. So with the understanding that is valid on the interval 0 to infinity, or the interval negative infinity 0, and so when you look at it, you're going to look at it this way, but it's still correct. Let's do another example. When you have trig, so remember when you have the trig, you need to review trig identities, right? So you can work with these trig integrals. So here we have cosine theta divided by sine square theta. We can split the sine square theta into sine times sine, and cosine divided by sine is cotangent. So and that will, the antiderivative is negative cosecant theta. You see, so you can come to these here, and you can get these ideas from here. So keep in mind this when you're working on that, because you need to come up with a form that is known, that you can take antiderivative to, and in the second level of calc you'll be using different techniques for integration, but this is the beginning of it. All right, so here don't forget the c. We talked about the c, that you may have different functions that all have same derivative. So the general way of writing it is plus c. And of course, if you have something like this, you can divide and you get these exponents, and from there you use the power to find the antiderivative, then use the upper limit and lower limit, and you calculate the value of the integral. So one thing we need to talk about is that part 2, that was f of x, the integral of f of x, and the upper limit is b, the lower limit is a. It gives us this capital B, the antiderivative, and minus capital F at a, which is the antiderivative at a. So we can write, because f prime equal to f, we can just actually write it directly. Instead having here f, we're going to have f prime, right? If we do this, then it's going to give us a nice form. So f prime represents the rate of change. We talked about that for the derivative with respect to x. And f of b minus f of a is the change in y when x changes from a to b, right? And that's, so if this is a and this is b, this is going to be f of a, and this is going to be f of b, right? So f of b minus f of a is just going to be that change in y with right? So the derivative, which is just going to be that change of y with respect to the change of x, because it's the rate of change. And of course, with the derivative, we talked about that instantaneous rate of change. So from there, we can come up with this theorem here, which is the net change theorem. So the integral of a rate of change is the net change, because you subtract the f of b minus f of a, which is the net change. And here, of course, you have the rate of change, so it makes this theorem the net change theorem. And it is helpful in applications. So if V of t is the volume of water in a reservoir at a time t, then its derivative is V prime, is the rate of change in which the water flows into the reservoir at time t. So if you set it this way, when you look at this integral, you're actually solving that difference between V at T2 and V at T1, right? This is similarly for, let's say, the problem of concentration or the problem of mass. So it can just apply directly. The rate of growth for population, you can just apply it directly. And more examples, right? So I left this just in case you're interested. Depends on your domain. You can see which one applies and to use. So let's look at the particular note here. Remember this graph when we talked about the integrals and what it represents and if the function is positive or negative. So let's look at this application if this function is the velocity, right? So you ask what is the, remember you have displacement gives you, derivative gives you velocity. So the antiderivative of the velocity should be displacement. So you look at in specifics here, the displacement from T1 to T2, because this function goes up and down, it is A1. We did that with the integrals and working with the areas. A1 minus A2 because A2 is under the x-axis, so it's going to be negative, plus A3 is positive. So displacement is A1 minus A2 plus A3. However, if you want to find the distance, which is positive, then you're going to take the absolute value of these VT. So you're adding A1 and A2 and A3. Right? So this will help you distinguish between what is a displacement and what is a distance. So if you have acceleration, we know the antiderivative is velocity, and that's a change of velocity there. So if we have an example with Vt equals t squared minus t minus 6, and t is between 1 and 4, we've done a few of these examples. We can solve what is that change between 1 and 4. Then you just do the antiderivative for t squared minus 1 minus 6. So that's a t cubed divided by 3. And I think this one should be a t, right? Not a 1. You know. And this should be t squared. Yeah, the antiderivative of this one is t cubed over 3. For this one is t squared over 2. And for this one, it's just 6t. And we're placed here, and we have the limits 1 and 4. So we get a number. So remember, if you have a definite integral, you come up with a number. If you have indefinite integral, it's going to be some type of function in general form. All right, so this means that the particle moved 4.5, right? So negative, so let's write it, negative 4.5. What does this mean? This means that the particle moves 4.5 meter towards the left. So that's the displacement now has a direction. The right is positive, the left is negative, unless the motion is up and down. If it bounces like up and down, then positive will be towards the up and negative will be down. All right, and that's from the equation 3, the distance traveled. you can solve this, investigate this equation, and find out that the intercepts. And when you found the intercepts, you can find how you're going to add the integrals in order to find the distance. Because you want to investigate whether the function stays above or not. If it doesn't stay above, that if you ask about the distance, then you need to use the absolute value and calculate these parts. So if you do that, you'll find that you need to add these two parts. So if you look closely to this function t squared minus t minus 6, if you solve it to 0, as given here, you'll find that, and I have the graph for it, that on the interval 1, 3, it's below the x-axis, and you can also solve this, as greater than or less than. Or if you graph it this way, you'll find the regular way. This is the vertex, so you see this is 1, 2, 4. That's what the two upper limits we're interested in. You see here, this part is below the x-axis. If it's below the x-axis, that means it gets subtracted when you use the kind of in the displacement. And here it's above. Maybe we should do a little bit this way. There's some approximation. So this is the 4, this is 3, this is 2. So from 1 to 3, it is below, which means this is negative gets subtracted in the calculation of displacement. And from 3 to 4 is positive, it means it adds up. So if you want to figure out the distance, this part we need to make positive. Well, how do you make the function there positive? You multiply it by -1 from the absolute value definition. So we know, let's put this here to the side. We know that the absolute value of A is A if A is positive. And we know the absolute value is of A, so we've done this one a few times, is negative A if A is negative. Why? Because you do negative A because A here is negative. Let's give it an example. Absolute value of 5 is 5 because A or 5 here is positive. But if it is negative 5, as we say negative, then you have to do negative 5 to make it positive, right? So that's one thing to keep in mind here. Absolute value of 5 is 5 because 5 is positive. But if the inside is negative, then it needs to be multiplied by negative, which means the opposite, to make it positive, you see. So here below, from 1 to 3, it's below the x-axis, which means it's negative. So the y function here, this y thing, if you want to make it positive, you need to multiply it by negative. And that's what happens here. This is what this does. We multiply the function by a negative and it changes, right? So we have t squared minus t minus 6 is negative 1 to 3. So to make it positive, you're going to multiply it by a negative, which means take its opposite, and that's going to change it there, right? So, and that's it. And you do the integral as usual, the antiderivative on it, and plus this other one is already positive, so that's not a problem there. The function there is positive. You see it? That stayed the same, because it stayed positive. And that's it. You do the evaluation on it, and you get 61/6, which is 10.17. So there is a difference between the displacement and the distance. The displacement um, is the integral, and uses whatever net area. However, for the distance, it needs the absolute value of that function. So you find where it is negative, and that part needs to become positive. So let's look at some examples from the homework. Let's say uh, let's say 3, just to practice indefinite integral. If you have 5b v squared plus 4. Of course, if you have these, you don't want to worry about whether the chain rule or something, you know that you can, of course, FOIL this one and distribute. Now the antiderivative of each one, this is indefinite integral, so don't forget you're going to have some c here, because that's indefinite integral, so you're going to end up with the function. So 5 is 6/6 plus 40/4 u squared over 2, so it'd be okay. So remember again, it's indefinite integral. We end up with some function here and plus c, because it's in general form. And you're going to keep the table or the graph or formula sheet in mind as you work on these, and the manipulations will help. So if you get something like this, instead looking into the formula sheet, do we have this one? Maybe let's look into simplifying it first by dividing by x. And that's going to be 7x squared minus 2x negative 1/2 by doing x 1/2 and minus 1. So it's going to be 7x third over 3 minus 2x 1/2 over 1/2 plus c. You'll also see it written this way, the third x cubed, and 2 times the 2 will be 4. Let's see, number 5, 2x squared plus 7 plus 7 over x squared plus 1 dx. So this is we're familiar with these, and of course this one you look at there and it's the inverse tan x plus c. Let's look at 9. We have 7 sine 2x over sine x dx. Based on the properties, we can put the sine outside, the 7 outside, and keep the sine 2x inside. And we have the double angle formula says the sine 2x is 2 sine x cosine x divided by sine x. That's going to be a 7. And now a 2 comes outside as well, cosine x dx. So it's 14. Now the antiderivative for cosine is going to be sine. So we can just go ahead and write it since we don't have a definite integral. So it's just going to be sine x plus c. Let's do 11. You see, these are not bad because you've done the big part of the differentiation. So, and of course, dr, you can write it on the side and with this 1 over, or you can just do that. But if you look at this, this is a definite integral. So we're going to do r sine of r because of dr there, and we'll use the limits. So we need these angles that have the sinus square root of 3 over 2 and 0, and of course within the restricted domains, and that's going to be pi over 3 minus 0, and that's going to be pi over 3. All right, thank you.